Oh, Mr. Yap, you look cool. Here, have this.
Oh, what's this, Mr. Liao?
Shake it. This is a heat pack.
Shake it.
Yeah.
Ooh, it's hot now.
Of course. The reason why is because the heat pack contains iron, and upon exposure to the atmosphere, it undergoes oxidation, and oxidation of iron is actually a exothermic process, which means that it releases a lot of energy, and that's why it feels hot.
Oh, you mean there's iron powder inside?
Yeah, why don't you just open it up and take a look? Go ahead. Oh wow, it's actually black in color.
Yes,
Yes.
iron.
Yeah, why don't you touch it? Take a look whether it's hot or not.
Is it safe or not?
It's safe, definitely. Trust me.
Whoa, 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 it's a bit too hot, oh my god.
Of course, because there's so much oxygen in the air, the iron oxidation is going to happen very readily, releasing a lot of heat.
Okay.
Hi guys! Today's lesson will be focusing on a new chapter called energetics, right? So the whole idea over here is that every chemical reaction, usually there's going to be accompanied by energy changes, right? The reaction sometimes could absorb energy or they release energy, and this is the reason why sometimes if you go and touch the solution or the reaction mixture, you realize that it gets hotter, or sometimes it could even get colder as well. Right? So how do we quantify this change in energy? We're going to use this term called an enthalpy, right? So enthalpy over here is generally denoted by the letter H. It is a measure of the energy or heat content of a particular substance. So the idea over here is if you have high enthalpy, it means that you have a lot of energy. And do you think this is stable or unstable, Mr. Yap?
High energy is like hyperactive like that, right? They cannot
Yes.
sit still, so it's not going to be stable.
That's right. So if you have high energy content, chances are you're going to be very unstable, and the vice versa will be true as well. Right? So we're going to take a look at the two different types of energy changes, whether is it endothermic or exothermic. So Mr. Yap, could you run us through this diagram over here?
Right. So I think most of you guys will be familiar with the term endothermic and exothermic since your secondary school days. But just very briefly, endothermic means heat enters the reaction. So the reactants gain energy to become the product. So the products will be of a higher energy level than the reactants. So if you talk about the enthalpy change, which is the product minus the reactant, okay, the enthalpy change is going to be a positive value.
That's right.
Now, heat enters the reaction. Where is this heat coming from? It's going to come from the surroundings. So the surrounding is going to lose heat energy, and therefore the temperature of the surrounding will drop. Now, take note, we always measure the temperature of the surroundings. We cannot measure the temperature of the reaction. So the surroundings could be, if it's in an aqueous solution, it will be the temperature of the aqueous solution. If it's in air or in normal atmosphere, it will be the temperature of the air around it. Okay, so that's an endothermic process. Now, the opposite, exothermic, heat exceeds the reaction. So reactants lose energy to become the product. So the product now is of a lower energy level than the reactant. So the enthalpy change is what we call negative. And heat exceeds the reaction, goes to the surrounding. So the surrounding temperature actually increase. Right.
That's right. So in this case, for endo and exo reactions, we also need to take a look at two very important diagrams.
Yep.
First of which is known as the energy profile diagram. Okay, so hopefully you recall energy profile diagram. Typical things is that there must be an x-axis, right? The x-axis, be careful, everybody highlight, it must be the progress of reaction.
Right.
And the second typical thing is that there's going to be a hump, right?
Yep.
You're going to see an increase and then come down to a minimum again, to a bottom again. In the case for our endothermic reaction, so we're going to see the two different features over here. The first of which is going to be the enthalpy change. And just now, Mr. Yap already told us that enthalpy change for endothermic reactions must be positive, which means that it's going to be represented by an upward arrow, right? The second thing is called the activation energy, which is represented by EA. Mr. Yap, can you run us through what is an EA then?
Right, so activation energy, the definition is given at the bottom of the page, but basically it's the minimum amount of energy that reactants must possess when they collide before a reaction can occur. Right, so it represents an energy barrier, essentially. Yeah.
So in terms of drawing the arrow, it must be a one-headed arrow that's going upwards to the maximum, starting from the reactants.
Yep.
Right? In the case for exothermic, of course, it's going to be the other way around, because exothermic reactions, you're going to see a negative enthalpy change. So it's a one-headed arrow pointing downwards, and of course, you're also going to see the activation energy. All right. Now, the second diagram that's important over here is called the energy level diagram. So I would think of this as a more condensed version of the energy profile diagram, of which, number one, you're not going to see an x-axis, right? There's no progress of reaction anymore. And number two, you're not going to see a hump over there. This diagram is purely going to represent the energy level of the reactants and the products, right? This is going to be very clear in terms of telling me who is more or less stable.
Yeah.
So if I take a look at the endothermic reaction, the product has a higher energy level,
Yep.
so would it
and
be
therefore
more?
it will be less stable.
That's right. And conversely, if you talk about your exothermic, who will be the one that's less stable?
So the product is of a lower energy level, so it's going to be more stable.
That's
so
right.
the reactants will be less stable.
That's right.
Yep.
So any kind of reaction, right, will involve bond breaking and bond forming, right? So can you tell me, is there an exo or endo reaction, Mr. Yap?
Right. So for bond breaking, you need to break the bond. You need to invest energy into it. So you need to take in energy. Heat needs to enter. So definitely bond breaking is going to be an endothermic reaction, and bond forming is the opposite. Therefore, exothermic.
That's right. So if you want, you can go and box this up. This is an important concept. We're going to see this quite often in some of the questions that we're going to see later.
Yep. Okay, Mr. Leong. So we got the next enthalpy change we're going to look at is called the standard enthalpy change of reaction. The definition is given at on the screen. This is a very important definition. Please go and memorize it. But essentially, the standard enthalpy change of reaction is the energy change involved when molar quantities of reactants, as specified in the equation, react to form products under conditions of 298 Kelvin and 1 bar. So you see the term underlined, molar quantities of reactants. What does that actually mean? Okay, so let's use an example to illustrate this. So if you were to look at this equation, if you look at the balance equation, the stoichiometric ratio is 2:1 for hydrogen and oxygen, but you're forming 2 moles of water. So what it means is when 2 moles of hydrogen react with 1 mole of oxygen to give you 2 moles of water, 572 kilojoules of energy will be released. So in this case, this kilojoules per mole, the per mole actually refers to per mole of the balance equation, so the stoichiometric ratios matter. Okay, so once again, it must be 2:1:2 in this case for the 572. Okay, now Mr. Leong, what about the second equation?
So if you look at the second equation, now I decide to halve all my stoichiometric coefficients. So now the coefficient is 1, half as well as 1 over here. So what do you expect to, how would you expect the delta H to change instead?
Right, so for 572 kilojoules of energy, the ratio must be 2:1:2, right? But since the ratio is now half, the delta H have to be half as well.
All right, that's good. So what happens if I decide to reverse the reaction? That means now I'm going to use water and break it down into their components.
Right, so if you reverse the equation, you flip the equation, the sign needs to be flipped, but the magnitude stays the same.
That's right. Now, the second thing that is important inside the definition over here, right, is that you're going to conduct this under a very specific condition of 1 bar and 298 Kelvin. So just to remind you again, bar refers to units for pressure, right? So this is what we call the standard conditions. So usually in standard conditions, we have to use this symbol over here, a circle with a line across, and we normally write it as a superscript, meaning that it's written at the top of your line, right? This is to represent standard conditions, which always has the standard value of 298 Kelvin, which is 25 degrees Celsius, 1 bar, which is 100,000 Pascal, and if you are doing aqueous solutions, right, the concentration of the solutes must be at 1 mole per dm cube. All right. Now, why is it important for us to define the standard conditions there? Is because the moment if I change any of this, then the enthalpy change will not be the same as well. So we'll illustrate this using an example at the top. So just now we were trying to form 1 mole of liquid water and it releases 286 kilojoules of energy. The moment you change it into a gas, right, you'll notice that the number is going to switch as well. Mr. Yap, can you remind me why is there a switch over here when you change the state?
Right, so when you change from liquid to gas, right, so you are going to use energy to vaporize the liquid. So some energy has to be used up to convert the liquid into gas. So that's why when you change from water to gas, the enthalpy change actually becomes less exothermic.
That's right. So the difference in this energy over here would represent the energy that you need to turn from the liquid into the gaseous state.
Yeah.
Now, one important thing as we write the equation is that for any kind of thermochemical equations in this chapter, we must always put in the state symbols, right? This is the reason why we told you that the difference in the states would actually affect the enthalpy change.
Yeah. So, enthalpy change of reactions are usually determined by experiments, but some reactions might be too dangerous to carry out because maybe they are too explosive. Mr. Leong, would you want to run such an experiment?
Probably not, right?
Right. If not, then how do we measure the enthalpy change of such an explosive reaction?
Don't know.
Then don't learn chemistry.
Okay, one gun. Hey, lunchtime. Hey, go. Okay. Go first.
Alright, so Mr. Leong, before we head for lunch, I'm going to issue you a challenge.
Okay, sure.
So both of us, we're going to start at this level.
Okay.
One of us is going to take the lift down.
Sure.
One of us is going to take the stairs down.
Sure.
Okay, we will see who reach below first.
Okay.
And the loser treats lunch. How does that sound?
Sure. Sounds exciting.
So let's play a game of scissors, paper, stone. The loser will treat lunch. The loser will take the stairs, sorry.
Oh, okay, sure.
Can I? Alright. I'm going to come out stone,
Oh, okay, sure. Can.
Okay, scissors, paper, stone. A best of 3 can?
Okay, sure. Let's go for it.
Okay, scissors, paper, stone.
So one each,
Okay. Last one, Scissors, paper, stone. You take
best
the
of
stairs.
5,
No.
Okay, so on the count of 3,
Sure.
1, 2, 3.
Round 1. Fight!
Oh my, the leak is not coming.
Oh my gosh.
Easy challenge. Take the stairs. Could be fall down. Easy challenge.
Oh,
What? Same time ah? Oh shit. It's a draw, I guess.
I think it's a draw. So who treat lunch?
Go Dutch ah.
Oh, okay. Okay.
Bye guys. So just now the analogy was just us trying to illustrate the idea of Hess Law. So what is Hess Law? The definition is given on the screen. So the enthalpy change for a particular reaction would be the same regardless of the route taken, provided that the initial and final conditions are the same. So just now the two of us, one of us took the lift down, one of us took the staircase down. We started at the same level, we ended at the same level, so the amount of time taken for both of us would be the same. So that's just one way of looking at Hess Law. Okay, now in terms of a second analogy, so if you were to look at this diagram in the middle of the screen, so let's say my house, okay, I stay at A, my school is at E. So your discipline master in school don't care how you go to school. You can take bus, okay, take from A to D, then you change your bus, go to school, then end up at E, or you could take an MRT or Grab, whatever, right? A to B, then go to E again. The discipline master doesn't care how you go to school. They only care that you arrived on school on time. So yeah, that's the analogy of Hess Law.
This is what we call path independent, right? You tell me that, hey, you go whether by the top route or the bottom route, as long as you hit the same location, you should be fine, right? Now let's take a look at a more technical aspect. So in the context of an energy cycle, right, one of the things that's important is to learn how to connect all these enthalpy changes together, right? So what we're going to do over here is we're going to use this method called the clockwise arrows equals to the counterclockwise arrows. So the first thing that we do is always to go and identify what is the center of the clock. So if I take a look at the top circle, right, obviously the center of the clock is going to be here, and I'm going to take a look at all these clockwise arrows. So Mr. Yap, can you share with me what is a clockwise direction first?
Oh, clockwise, very simple. So this is a clock, right? So clockwise is like that.
Oh, okay.
Sorry.
Thank you.
So that's the clockwise arrow.
Yes. So can you answer my question? Who are clockwise arrows?
Oh, so delta H3 and delta H4 will be the clockwise arrows.
That's right. So what I'll do is I'll take these two enthalpy changes and add it up together because they are all in a clockwise manner, right? How about the anti-clockwise ones then?
Right, so you'll be delta H and delta H5.
These two, right? So I'll add these two together, delta H and delta H5. Now, Hess Law tells me that they are going to be equated to each other. So therefore, you can equate them. And let's say if you are trying to find out what's the enthalpy change over here, the delta H, you can make delta H a subject of the formula, bearing in mind that the rest of the enthalpy changes are already known. So this is the application of the Hess Law. Shall we take a look at an example? Now, let's say I want to find out the enthalpy change of this particular reaction itself. You say that there's going to be some problems with this reaction. Mr. Yap, can you share with me what's wrong with this?
Right, so this equation produces carbon monoxide, right? So carbon monoxide is a toxic gas. I don't think we want to deal with that, right?
Yeah, that's right. So therefore, we say that we are not going to do this in a lab. We are going to use two other equations to help me to go and find out the enthalpy change instead. So I have three equations down here. So I'm going to label them so you can just number them together with me, 1, 2, and 3. Now, I need to learn to connect all these three equations together. Mr. Yap, what do you think is the best way to do that?
To connect them together, I think we have to draw an energy cycle.
That's right. So now we are going to introduce you the steps to drawing an energy cycle. So this is pretty methodical, so just follow me closely with this. So the first step, right, is this. Every single time when you start off with an energy cycle question, always go and write out the balance equation. And like we mentioned earlier, we definitely need to put in the state symbols, right? Why is that so, Mr. Yap?
Right, the state symbols would affect the enthalpy change of the reaction. So the state symbols are absolutely important in this case.
That's right. So this chapter, every single time I ask you about equation, you must put in the state symbols. Okay. Now the second step, right, is going to be a bit new for you. We're going to start off with this thing called the most complicated equation. Now what do I mean by that? So generally, most complicated, you should be able to tell, it should be the one that probably has the most number of atoms, or the stoichiometry is actually going to be the largest, right? So very easily, let's take a look at 1, 2, 3, Mr. Yap. Which one do you think looks the most complicated?
Wow, all looks complicated to me. Chemistry is hard.
Yes, but what's the most lah?
Okay, equation 2 is the most complicated one.
So equation 2 is the most complicated, and what I'll do over here is I'll write out this equation first. Okay, so you can follow together with me. 2CO plus O2. Bear in mind that I must write in all the state symbols as well, right? And from here, I'm going to put in the enthalpy change at the top of the arrow.
Yep.
Okay. Now the moment I've done this equation, I'm going to take it off because I've already applied it.
Yep.
Now the next job over here is to look at equation 1 and 3, and we want to see which one can easily link into the red equation that I've drawn earlier.
Yep.
So Mr. Yap, what do you think?
Okay, so if you were to focus on the right-hand side of the equation, you would notice that you are forming carbon dioxide, right?
That's right.
And if you were to look at the information given, equation 1 is also forming carbon dioxide. So we could say that we could write carbon and oxygen at the bottom, and we could draw an arrow pointing upwards and say that represents equation 1.
That's right. So this equation itself is a bit problematic because here I'm trying to form 2 carbon dioxide,
Okay,
right?
okay.
But equation 1 only has 1. So what do you suggest we do then?
Times 2 lor.
Times 2. So I times 2 here, times 2 here, times 2 here. This one you times 2 or not, enthalpy change.
Of course.
Right? So this is exactly what we mentioned earlier. You tell me that it's dependent on the stoichiometry.
Stoichiometric ratio, yeah.
That's right. So I'm ready, yeah? This arrow is pointing towards 2 CO2. I'm going to point an arrow towards 2 CO2 and write in 2 carbon. Okay, 2 carbon, give me 2 oxygen over here.
Yep.
All right. Now, this one, don't forget to go and put in the enthalpy change. And this one, do remember that you must put in the 2 as well, the multiplier. Okay, so I'm done with equation 1. I'm going to take equation 1, and we're only left with equation 3 then, right? So for equation 3, once again, you have to pay attention to the direction of the arrows.
Yes.
We are pointing towards the 2 carbon monoxide, and as a result, if I take a look at the connecting the whole cycle together, 2 carbon dioxide, we are going to point it towards that. So if I were to pay attention again, 2 carbon and 1 oxygen is going to react. So if I look at the reactants, 2 carbon, and if I look at the oxygen, right, there are 2 over here. But you're only using up 1.
Yep.
What does that mean, Mr. Yap?
So basically the oxygen is in excess. So the other oxygen that is not used will merely be just carried forward. So that's why it appears in the equation on top.
So therefore, you can notice that in every single portion of your energy cycle, all the atoms will actually balance, right? Now, we have an energy cycle. I'm very happy, but I still need to go and find out this enthalpy change, right? Which I put this as delta H. What must I do at the last step?
You can do your apply Hess Law and do your clockwise, anti-clockwise thing, right?
You don't need to hit me all the time every time you say that. Okay, but anyway, yes, we're going to apply clockwise equals to anti-clockwise. So once again, identify the center of my energy cycle and tell me the clockwise arrows.
So the clockwise arrows would be the delta H and negative 566.
So I'll add up these 2 numbers together, right? So I'll add negative 566. And what about the anti-clockwise ones?
Right, the other one. So 2 times negative 393.
That's right. And from here, you set up a linear equation. You can solve for delta H, and that will be the answer that you see on your notes over here. So this is something that you can understand, but definitely is more important for you to try it out. So therefore, in class, we're going to try out a few questions so that you can apply all these concepts.
Okay. See you guys in class.